let us now discuss some slightly more elaborated examples of the saddle point approximation. So let us consider the following integral with a large parameter lambda, which is assumed to be positive. So, and now main ingredient of our integral will be the fact that it is now evaluated in the finite portion of the real domain. And we will be interested in the leading term of the asymptotic expansion in lambda. So, of course, when you are dealing with such an integral, first of all, the most important thing to do is to choose a proper proper definition of the branch of the square root function. And we will assume that when this integral is written, it makes sense to assume that this is just an arithmetic square root for z real and between -1 and 1. And to make this meaningful for arbitrary z, it is convenient to make a cut from -1 to 1 with upper part of the cut the value of square root to be defined according to its arithmetic value. So now we integrate along this path. This is complex plane of z. And so here is our large parameter. And let us now figure out what are the saddle points, first of all. And they are defined, as usual, by the stationary points of the prefactor of the large parameter and the exponent. So we need to solve the following equation. D over dz of z cube plus 3z equal to 0. And the equation is, of course, nothing but 1 plus z squared equal to 0. And it has two solutions, z equal to plus or minus I. So here are the saddle points. And we need to understand how exactly we should deform our original integration contour to something which passes through the saddle points. We don't know in advance which one we have to choose, and how to evaluate the leading term of the asymptotic expansion. So, let us formulate a general rule which we will now apply for this particular case. And the general rule is such that we need to find all surfaces of the constant imaginary part of the exponential. So in other words, for this case, we need to find such lines in the complex plane which satisfy the following equation equal to constant. And of course, lambda just is not, sorry for that, this is z. And of course, lambda is not important for this criteria at all because it has a real part and it doesn't matter. So this equation defines a set. Of course, there are many curves on the complex plane z which satisfy this equation. So it defines a set of lines in the complex plane which are called stationary, which are called constant phase lines. And now we need to understand which of these lines, defined according to this equation, pass through, first of all, saddle points, and second, through boundary points of our integration domain. Let us solve this equation explicitly, assuming that z equal to x plus iy, where x and y are both real. And in order to resolve this, note that immediately it becomes the following expression. So the real part should be constant. And in other words, going even further, we figure out that the equation becomes and now we need to choose such lines of that class which pass through either saddle points or endpoints of our integration domain. And as an exercise, you can resolve this equation yourself. And let me draw just the result. And it happens that the curves of constant phase which pass through the boundary points behave like that. And there are also curves which pass through the saddle points, and they behave like that. now we're coming to an interesting question. So we know that integration along this path is simple. In fact, if you integrate along this path, the integral becomes almost real, because expression in the exponent acquires constant phase and just factors out of the integral. Some remnants of the imaginarity remain because you are dealing with integration measure and pre-exponential factor, but they're not so important as they don't have any huge oscillation, which becomes more and more dramatic with lambda. So the integration over this path is drastically simplified. And now we need to deform our original integration path to set of paths which coincide with piecewisely with these constant phase lines. And there are actually two ways to do this in this particular case. First way is to start from -1, go to -infinity like that, and finally like this. And there is of course another way. Let me draw it in some different color. So we can actually go to infinity like that, then pass the upper saddle point, and then go to 1 again. So there are two alternative ways to deform our integration contour. Obviously, they are very different, and actually only one of them is perfectly legitimate, because you can check yourself, and for this you need to analyze the real part of the expression in the exponential, which determines the convergence properties of this integral. And after analyzing the real part of this expression, you will find that actually the integral which goes to infinity like that actually diverges, and is not this integration contour is not legitimate one. But with the same logic, you can convince yourself that integration over both of these three segments is perfectly convergent. So we need to choose the second way of contour deformation. And now we are coming to more or less final point. We deformed our original integral, and remember it was highly oscillating because of this expression in the exponent, to a set of three integrals. Each of them is quite smooth and without any pathology in the limit of large lambda. And this is the greatest achievement because we explicitly found it was possible because we explicitly found lines of the constant imaginary path. But now we still have to estimate these integrals one by one. And let us call this, say, integral I1, I2, and I3. And in principle, our original function I is now decomposed into three contributions. Now we are coming to an important point. We need to decide for ourselves which is actually the dominating one. And in order to understand that, recall our general method for calculation of the asymptotics. And now please observe that this couple of integrals is very different from this one. In fact, the most important difference between them is that I2 is effectively an integral with which is evaluated over infinite domain, and I1 and I3 are evaluated over finite domains. So we know from the Laplace discussion of the Laplace technique that the methods for estimations of these two types of integrals are very different. So for example, let us now discuss, as a first case, let us discuss evaluation of I2. And this is typical integral to be evaluated by a saddle point approximation. And the first step in evaluation of such an integral is to estimate the exponent at the location of the saddle point. In fact, let us take this z cube plus 3z times lambda at the saddle point. And let us see what it becomes. So this is nothing but minus I, and this is 3I. So in total, this becomes exponent of minus 2 lambda. And obviously at large lambda, this is an exponentially small expression. Full evaluation along this contour also provides some factor, which is a power law function of lambda, and in principle generates a whole series of these powers with different coefficients. But as a first guess, we can understand that by an order of magnitude, this will be exponentially small number. And let us now take a look at the second contribution. So actually I1 and I2. And let us see what is the value of the exponent at the endpoint of the integral. And in fact, it is a much more pleasant one. And it actually, it becomes, if we substitute now z equal to -1 into the same expression, this just becomes -1 minus 3 lambda, which is nothing but exponent of -4i lambda. So obviously, this part of the integral described by I1 and I3 and as contributed by the endpoints doesn't have any particular smallness. This is just slowly, okay, still this is a function which depends very strongly on lambda, but this dependence is simply oscillating one. And again, full evaluation along this line will give us some power law prefactor. But already on this level, we see that in this situation, we have to conclude that this segment, I2, contributes exponentially small term, and this contributes something which is doesn't have any exponential smallness. So obviously, we need to concentrate on evaluation of these two segments. So let's proceed with that. Just небольшая пауза.